Mycket varmt välkomna till Vetenskapens hus och till dagens populärvetenskapliga lunchföreläsning. And a special welcome to Alberto Vomiero, who you will meet today. But I'll start my introduction in Swedish. So if any of you are English speaking, please excuse me. Universitetet tillsammans med Ingenjörsvetenskapsakademin och LKAB öppnade det här huset för 3,5 år sedan. 3,5 år sedan. För att ha som plattform för att berätta om den forskning vi bedriver och för att dela med oss av våra kontakter. Och även att vara en aktiv del i Luleå. Vi är väldigt glada över att vi får möjlighet att använda det här fantastiska huset som har stått här sedan 1953. Ett värdigt hus med ryggrad, sa en av våra inredningsarkitekter. Och vi hoppas och tror att vi fyller det med kunskap och forskning också med ryggrad. Jag heter Zoe Lundqvist och jag är ansvarig för universitetets populärvetenskapliga föreläsningar. Idag har vi en lite ovanlig riggning eftersom den här vackra skärmen, stora fina skärmen här bakom, den klappade ihop igår. Så att vi använder istället den här lilla skärmen. Och därför är det jättebra för er att ni sitter långt fram. Vi filmar också föreläsningen precis som alla andra föreläsningar. Och på det sättet kommer vi att klippa in Albertos presentation i filmen. Så ni har möjlighet att se den även i det formatet. Vi har haft en äventyrlig vecka här i huset. I tisdags klappade ljudet ihop. Och igår klappade skärmen ihop. Så att det är nog kanske dags för lite höstförnyelse även i Vetenskapens hus. Vi arbetar med projektet och det kommer att vara löst så snart som möjligt. Universitetets uppgift i Luleå, universitetens uppgift överhuvudtaget, vars vi än finns, det är att utbilda och forska. Och de två faktorerna är intimt sammanknippande. Du kan inte ge utbildning på hög nivå utan aktuell forskning. Och aktuell forskning behöver föras vidare till våra studenter. En ytterligare uppgift för oss är naturligtvis att vara just den aktiva del av samhället som jag nämnde. Att dela med oss av det vi kan, att dela med oss av vårt nätverk. Den här hösten så har vi 2 serier föreläsningar. På onsdagar pratar vi om lärande i olika former. Och torsdagar så presenterar vi ett forskningsområde som heter förnybar energi. In this area, Center of Excellence Renewable Energy, we have come to our 3rd lecture, I think. And today, the guest today is Alberto Vomiero, professor in experimental physics at University of Luleå. You will today talk about new research on solar cells and advanced nanomaterials. Is that correct? Then I wish you a pleasant lunch, an interesting lecture, and say welcome, Alberto.
So thank you very much, Zoe, for your very kind introduction. And thank you to LTU to give me the possibility of illustrating a few results of my research and to draft a panorama about technology and advanced in research in solar cell. My research is mainly focused on nanomaterials for advanced solar cells. I will try to give you a brief introduction on what's the present status of this technology and what is the research aims for the future. I started working on nanomaterials for environmental applications, fascinated by a paper from Boulding. He's an economist at University of Colorado, and he tried to imagine the Earth as a spaceship. And there are a few number of inhabitants, and the inhabitants are increasing pretty suddenly. Unfortunately, this space ship has only partially renewable resources, and we are struggling to try to use at the best we can a few renewable resources and try not to consume all the not renewable sources, mainly of energy, and we will see why energy is so important. Unfortunately, a few estimates from the National Academy of Science of USA were estimating that in 1961 we were at 70% of recovery of what we were able to use, while unfortunately at the end of the last century we were over 100%, which is not a good message for us, which means that we are wasting more than what we are able to recover. And these are pretty precise estimates from these scientists, and I will try to be precise in citations of sources about this, because they have a pretty high important societal impact. The importance of energy is mainly related on population growth. If you analyze the growth of the population in the Earth, it's mainly related on how much energy is available per inhabitant. So essentially the population started growing suddenly around at the beginning, in the middle of the 19th century, during the Industrial Revolution, which I would call, rather than Industrial Revolution, it's the Energy Revolution. And right now it's still increasing, with a few significant differences between the so-called developed countries and developing countries. Even if, for instance, China was considered developing countries, but right now it's pretty much developed. But it's one of the main contributors to the growth of the people in the Earth. And so this trend is challenging us to find a solution on how to deliver all the energy we need and try to support the growth of the population. And this raises a pretty high political and societal issue, not only a scientific one. There is another very open issue which is affecting the quality of our life, and it's climate change. Of course, during the different eras in the Earth, we had several climate changes, but it's pretty clear to the climate science community that the changes that we have observed in the last past decades are mainly caused by the human activity. And it's not only scientists that are saying that, but also pretty highly authoritative agencies like NASA, that has programs that are monitoring all the main effects of human activities for greenhouse gases, or the increase of carbon, or the level of ice and ice melting, and lately some atmospheric phenomena like hurricanes and so on and so forth. So it's not just a matter of being ecologists, it's just a matter of reading data and accepting data. Of course, we can comment that a few days ago the commander-in-chief of NASA was not agreeing with these conclusions, so the debate is pretty open about that. But so the question is, can we safely drive our life and trying to survive in the beautiful Earth? Well, it's not only a scientific issue, it's also a political one. And the good point is that in 2015, most of the world leaders agreed about a few goals, 17 goals for the sustainable development. And these goals are related with almost all the aspects of our life. And I personally, as a scientist, I'm focused on just a small part of it, which is the affordable and clean energy, which is the goal number 7, and specifically I'm focusing on solar energy. What solar energy? Well, it's originated from the thermonuclear reactions in the sun, essentially the fusion which is occurring in the sun, and it represents almost the entire electromagnetic spectrum, so from the visible light to infrared light, UV light, and so on and so forth, and is powering the life since millions of years. Using solar energy for producing energy for the man is not a new idea. It was from Thomas Edison much before then the photovoltaic effect was discovered, and it was in the middle of 19th century. So the history of using the sun to produce electricity and powering machines is pretty old. Of course, it's not an optimum energy source, even if it's fully renewable. There are advantages and disadvantages in this kind of technique. Luckily, the byproducts of nuclear reaction remain confined in the sun. Only pure radiation is reaching the Earth, and the amount of energy that we are receiving is incredible. It's much more than we need to power the humanity since the end of the world, probably. Unfortunately, the disadvantages are that the sun is not shining consistently, for instance, during the night, and the solar energy is a diffused source, so we need to transform it, to transport it, and to store it. And I would say that today the main open issue with energy is not really the transformation of sun power from light to electricity, but rather to store the electricity that we have produced to be used when we need it. So we are trying to address these disadvantages by improving energy collection, conversion, and storage. And from this point of view, I would say that people working in solar cells has not the hardest task, which is probably on energy storage right now. And another drawback is that 70% of solar energy comes roughly from the middle 6 months in the year, and this is for a particular latitude, but even here it's almost the same, concentrated in 6 months. So essentially the man tried to use in 2 ways the solar power. One is by exploiting it as thermal energy, and another one is through the photovoltaic effect. Of course, just trying to absorb the light and heating water is much easier than transforming it into electric power, but still can be done quite efficiently, and it has pretty long history since the beginning of the previous century. And also nowadays you can find pretty useful applications of this solar thermal energy. Today instead we will focus on the second aspect, so the photovoltaic effect, in which you are able to absorb a photon, to transform it into electric power, and to use electric power to powering external loads. I think, well, of course, this is a sort of 100% renewable energy, but the main question to me is it affordable and reliable? Because it's feasible for sure from a technical point of view, but what can we do, and is it sustainable for the future? So it's interesting that the International Energy Agency is publishing yearly a report on the renewable energy, and they are trying to compare how much is the share in the market of renewable energy sources divided by of course different kind of renewable sources, and how are they increasing compared to traditional sources. So the main question is, does it work? And if we look just to the increase of the installed power, you see that for most of many renewable sources like photovoltaics or wind energy, for instance, it's more than what they are installing, for instance, for new coal and gas factories. So from this point of view, it means that in the world, people is installing more energy coming from renewables than from traditional sources. And I think it's a good news. And if we consider the other point, what are the technologies that can help more, you see that essentially it is the wind, the sun, and the hydropower. So I don't think we just focus on one technology, and it's a very good way, but we have to try to spread the needs and trying to put together what we can do in through different ways of using the sources. So does it work? Probably yes, in my opinion, based on the data I've presented to you. The good point is that you can produce electricity by coal, for sure. It's produced roughly the 40% of global energy, so it's a huge amount. But it's responsible for 70% of greenhouse emissions related to energy. So you can say, I don't care. I mean, US took a decision 2 days ago just to start producing again and investing in coal. That's a legitimate decision, but you know that you will for sure increase the green emissions, let's say, in the next 10 years. The good point from the UK Energy Research Centre is that it seems that investing in renewable energy can be economically viable, because you can create a job market 10 times higher than when you invest the same amount of money in traditional energies. That's pretty interesting from the developing point of view. Scientists, it was a service published in Science a few years ago, tried to give a provocation. He said, we don't need too much room in the earth to produce the energy we need. You just keep an average solar cell in the market, 10% efficiency, and what you get is that you essentially can power all the earth. Of course, it's just a provocation, because you cannot store and transport this energy. But the message is that if the technology is able to supply the energy we need, we can really use it in a very useful way. I'm not an expert in energy markets. And if you look at the global picture of what's going on in energy, it's really very complex. So we will focus today just on a very small part, which is nanomaterials for solar cells. So of course I miss somehow the big picture. We try to keep in mind, but it's pretty challenging on that. So I've just given this brief introduction, and I understand it's not conclusive on that, but I hope it helped to understand what's going on in our research. So coming specifically to solar cells, the operating principle of solar cells, of standard solar cells, is pretty simple from the engineering point of view. You have two materials that can be very similar as a compositional point of view, but they have, let's say, a different behavior from the electrical point of view. Typically, you have semiconductors, which are the same as you find in the chip of your computers, that can either have an excess of electrons or a loss of electrons. So you can call them p-type doped or n-type doped semiconductors. When you put together these two different materials, you create an electric field in between this junction, and this field is able to separate the charges that you can create. And you can create the charges essentially because these materials are, let's say, colored, so they can absorb the sunlight. So you absorb the sunlight, the photon is absorbed, and this photon is transformed in charges, and the electric field which is inside this junction is able to separate these charges and to give rise to electric current and electric power. So how it works, essentially you have 4 different physical or chemical processes involved. You need to absorb the light, to separate the charge, to generate the charge, to separate them, and to collect to the external circuitry. And all the advancements in technology of solar cells rely with one or more of these 4 processes, trying to improve the light absorbance, so creating materials with different colors, absorbing from the infrared region to the UV ultraviolet region, or to increase the production of charges. So you just have one ray of light, you want to create probably more than 1 electron per photon, or separate better this charge and better collect this charge. And along the times, I would say in the last 70 years, we've seen the development of mainly 3 generations of solar cells. So the first generation was the one who has the highest market share, around 70%, which is based on silicon. And essentially they started with silicon thanks to the microelectronics industry. So you have 2 different kinds of silicon solar cells, either single crystalline bulk silicon or polycrystalline silicon. The main issue with this kind of solar cells is the cost, but the photoconversion efficiency, so the power you can extract from these cells is pretty high. It's around between 14 and 20%. At the lab scale you can produce 27% efficient silicon solar cells, which is pretty good, but the cost is high. So people tried to substitute these crystalline materials with thin film materials that can be produced with much cheaper processes, and you need much less materials. Instead of, let's say, 5 micrometers of silicon, you can get, let's say, half micrometer of thin films, and with an operating for getting an operating device. So you reduce significantly the cost, but unfortunately you reduce also the photoconversion efficiency, so the panels are less efficient than silicon. But still you can find in the market amorphous silicon solar cells, or copper indium gallium selenide, or cadmium telluride solar cells. As you see here, in a few cases you have environmentally harmful materials like cadmium, but still they are in the market, and one of the most successful company is promising to keep back the solar panels after they expire. Of course they are lasting 20 years, so you are not sure if a company will be in the market after 20 years. But and after this second generation, there will be the 3rd generation solar cell, because essentially scientists, when they want to invent something new, they say it's a new generation. So roughly 15 years ago started circulating this concept of a 3rd generation, which puts together different kinds of solar cells. Here I'm reporting multi-junction solar cell, which is at present the most efficient solar cell, not in the market because you cannot find it. It's for niche applications in satellites. The concept is that the light of the sun has different colors, and you can absorb each color with a suitable material. So you have 3 or 4 different materials, each absorbing the specific part of the spectrum and letting the other part to penetrate for the next absorption. And you can get a photoconversion efficiency roughly about 47%, which is crazily high in these kind of materials. but the structure is pretty expensive, so it's limited to a space application, essentially. Another structure you can find is a concentrator solar cell, which is using the concept of multi-junction solar cells, but they say the solar cell itself is too expensive. So we try to use a small solar cell and concentrate to it a lot of light radiation through a pretty cheap mirror, a concentrating mirror. You can get concentrations up to 100 times the sun intensity, so it's pretty intense beam. The drawback of this application is that you need to follow the sun with pretty precise stepping motors. So it's the main drawback of this technology, but still you can find operating some parks with concentrating solar cells. And then we have two other, let's say, low-cost solar cell, polymeric solar cells, so plastic cells. Unfortunately, they are limited in efficiency, which is around 10–12%, and in durability, because indeed they are made of plastics. But of course, if they are really very cheap, they can be used for specific application. And other kinds of solar cells, which are the solar cells I'm also involved in, excitonic solar cells, in which you see different kinds of materials. And the nice part here is that different materials are doing different tasks in the system. So one material is absorbing the light, another one is transporting the charge, and another one is neutralizing the light absorber after you have extracted the charge. And so you can play and try to optimize different parameters in this solar cell. And these kind of solar cells are pretty cheap. The efficiency is not so high, so you cannot even find them in the market. But one of the main concepts is that different types of solar cells can be applied for different applications. So in satellites you can have very expensive solar cells, but if you go with the so-called building integrated photovoltaics, you want to have a colored solar cell. The efficiency is not so critical, so dye sensitized solar cells are very nice because they can be, as you see here, green, yellow, red, and so on. Architects are very happy about that. Or you can have portable devices or off-grid applications in the developing countries. So depending on the application, you can really find the most suitable for a solar cell for you. And this is a kind of a scheme that scientists would like to develop. So you have a first generation solar cell which has pretty high photoconversion efficiency, but at high cost. The second generation has lower efficiency at reduced cost. And of course, you see here, number 3 is a dream. It's not the reality. We would like to have high efficiency at low cost. Up to now, we are in the upper right part of the diagram, so we can have high efficiency 47 but at high cost, and we are struggling to reduce the cost or to increase the efficiency of low efficiency solar cells. So one could tell us, why do we need research in that if since 40 years you can find good silicon solar cells in the market? And you can see here the National Renewable Energy Lab in US is publishing yearly the certified efficiency of solar cells and its increase according to the years. And you see that for several technologies the increase is very steep in the last years. And all the increase you can see in the efficiency is mainly due, it's exclusively due, I would say, to technology research and basic science. So the advancement in this sector is really related to the development of new materials and nanomaterials. And let me come now why we wanted to use nanomaterials for this kind of solar cells, and this will be the second part of my presentation. So Xiaopeng in Nano Research in 2009 was asking himself, is there a role for the scientists in this development? Okay, he is a chemist, I'm a physicist, so we are struggling with each other, but I quote his conclusions. He said, yes, we can work, and nanomaterials are very important to boost the efficiency of these kind of devices, and not only in the energy system, I would say. Let me give you a specific example. If you keep, let's say, a grain of sand, kind of 1 millimeter by 1 millimeter by 1 millimeter in volume, and you try, so the volume is constant, and you are able to divide it and divide and divide. What you increase is the surface you are able to create inside this material. Sorry. So, for a practical example, let's make the hypothesis of dividing 12 times 1 millimeter cube of material, and what you get that for 1 millimeter cube you have 6 millimeter square of a surface, but if you divide it 12 times you have more than 24,000 millimeter square of surface in the same volume of material. And that's very important because in solar cells, for instance, the absorbed light is proportional to the specific surface of your material. It means that you increase the light absorbance of a factor roughly 5,000. Okay, and that really works. So are we able to do this division of materials and to create new nanostructured materials? Luckily the answer is yes. Then it comes to the problem with the functional properties of these materials. And in fact we can create nice shapes of different compositions. Here we are indium oxide nanotubes, here we have the titanium nanocubes, titanium oxide nanotubes, so we have zinc oxide cubes, and you can see that there is a nanostructure in them, so you're easily able to produce let's say 20 nanometers nanoparticles aggregated together and forming a well-structured material. And so I will give you now a few examples how playing with nanomaterials you can improve light absorption, increase the charge generation, enhance the charge mobility and electron collection, and exploit new geometries, which were the 4 topics related to transform the sunlight into electricity. So to improve light absorption, for instance, the problem is that if your material is not enough absorbing the light, you lose part of the light as transmitted light. In some cases it's good, because if you want to have, for instance, a red window, you want that part of the light comes to you inside, otherwise it's completely black. But in some other cases, like the solar cells in the roof, you don't care about transmitted lights, it's only energy which is lost. And there was a very talented scientist, Diedrich Wisma. By accident, he's now working in Italy, one of the few attracted brains from Poland to Italy. And he suggested theoretically that if you use a disordered network of materials, you can trap the light and increase the absorbance. And he published it in Nature. So we said, no, we don't like Nature, let's go with lower journals. And we tried to apply experimentally his idea, proposing a solar cell in which you have these large aggregates composed of very small tiny nanoparticles, so we can trap the light and increase light absorbance. And our chemistry guys in the group were very happy because we published it in Angewandte Chemie, which is a chemistry journal. Of course it's not Nature, but we are happy anyway. And we demonstrated that by tuning these properties you can really increase the photoconversion efficiency. If you look at the numbers, it's 7.5% of the maximum you get. And of course you can tell me, but if you use silicon, you can easily get 14 or 18%. That's true. But our cell, luckily, was really very cheap in this respect. And how to improve light absorption? Another concept is the concept of luminescent solar concentrators. Luminescent solar concentrators are roughly plastic slides in which you can absorb the light, but there is a colored element inside which can re-emit the light. And as you can see, the light is re-emitted and collected only at the boundary of your slice of material. And in this part of material, you can place a solar cell and transform part of the light into electricity, which is the concept that they developed at Palais de Congrès de Montreal, in which they were using these colored windows. So part of the energy is released and is transmitted as a colored light, and part of the energy can be used for powering solar cells. For this application, one of the most effective materials is this kind of guys. These are quantum dots, which are very small particles between, let's say, 2 to 9 nanometers, which have very interesting optical properties. You can see here, you can tune the color of these particles by simply tuning their size. So you change the size and you change the color, which is very important because it means that you can absorb the sunlight in different parts of the solar spectrum just by changing the size of your particle, which is not particularly demanding from the technical point of view. In our previous case, let me say that the most challenging part was not to create this quantum dot, but was to create a core shell structure. You can see here in the center a very bright spot. This is the core of this particle, which has a composition. It's a lead sulfide. And the other part of the quantum dot has another composition. It's a protecting shell of cadmium sulfide. Well, detecting this lead sulfide inside this larger volume of cadmium sulfide was pretty challenging. So it's not always easy to get these results. And our colleagues working in microscopy were struggling for let's say a few months to get these results, but at the end we were very happy of what we were able to demonstrate. So I already told you you can tune the color of these nanoparticles just changing the size, and this is very important because by changing the size somehow you change the ability of these crystals to create the charge, but also to inject the charge from them to the other material who is able to transport the charge. And that's pretty critical from this point of view, because you could say, well, I want to use a crystal which absorbs all the sunlight, but if you use that kind of crystal, is not able to inject the charge to the other material. So unfortunately in this field you have to try the best compromise, which is not the best solution for all the processes. So there is no solution in which you can absorb fully the light, don't disperse any energy during transport or injection or collection. And I think this part of the panel in the bottom right gives you an idea how it works. If you see, we have different compositions of these cadmium sulfide, lead sulfide materials, and the best is in the middle. And in the middle, unfortunately, you don't absorb all the light, but you maximize the ability of transforming the sun power to electricity. Another way in which nanomaterials are very important is, for instance, by using elongated one-dimensional structures. It's pretty clear that when you use mesoporous materials and you have to collect charges, that's a very challenging process, because the charges are hopping from particle to particles, even several thousands of times. So in 2005, Professor Peidong Yang from Berkeley was proposing, why don't we use this elongated structure? At the beginning, it was a pioneer in the growth of these nanowires. Now it's pretty consolidated technology. And the benefit of nanowires is that once your charge is inside the nanowire, you can straightforward collect it without any hopping process. So the probability of losing this charge is much reduced. And in fact, they were able to demonstrate that by using this kind of wires, they were increasing the photoconversion efficiency. And we tried to do the same using carbon-based materials, either using carbon nanotubes or using graphene sheet. Graphene, which was awarded with a Nobel Prize in 2010, and the professor who was the chair of Nobel Prize in that year now is guest professor at LTU is Ingemar Lundström, so we're very honored at that. Graphene is a single layer of carbon atom which are distributed orderly in an hexagonal pattern, and the conductivity can be much higher than composite materials or mesoporous films. So we tried to put together these graphene sheets and titanium oxide particles, and we demonstrated that it's very useful to increase the photoconversion efficiency. And just another example, one of the last, we wanted to try to exploit new geometries by using nanomaterials that can be deposited on plastic substrates for portable applications. Of course, in this case, you don't require a durability like a solar cell in the roof. You don't expect your bag is lasting 20 years. So when your bag and your solar cell related is lasting 2 years, it's okay for the market. Even if after 1.5 years the solar cell is gone, but the bag is still there, sometimes you can place it in the market. And in fact, this is the duration they want to guarantee. And we were able to do that by depositing titanium oxide nanotubes on a plastic substrate. The good point for using these kind of tubes compared to the nanoparticles is that when you put together nanoparticles, you have to heat them at around 500 degrees to sinter them and to obtain the film you want. While if you grow these nanotubes, they have already ordered after the synthesis, and you don't need to treat them with, let's say, post-heating treatment that can destroy your plastic. So you can get a plastic substrate with an operating solar cell, almost working. The efficiency was not so great at the time, but it was comparable with the efficiency that they got with the same tubes, but on titanium foil. And we got on a polyimide foil, which is a plastic which is pretty resistant. So we were happy because you can claim that a titanium foil is flexible, but you cannot apply it as a portable electronics for sure. So after these examples, I would like to come back and check. My first question is the technology helpful for developing the solar cells? And I would say yes, in the sense that almost all the results that I have illustrated to you and that brought to record efficiencies in solar cells, even if we are not here in the table, but colleagues that are working on similar topics are here. If you look, for instance, University of Toronto, they are producing top world record solar cells on quantum dots, or new kinds of perovskite solar cells that are made of very promising material. They got 20% efficiency coming from 11%, and the jump was more than 7% in efficiency in just 3 years. Unfortunately, these cells are absolutely unstable. So from a market point of view, it's not a good news. It's a good news for researchers that can continue working, but from the market we are still waiting for stabilization of this kind of solar cells. So my answer is definitively that the advancement in this sector is mainly based on the development of new nanomaterials. And this is also our purpose at LTU, in which since the launch of a chair 3 years ago, we paralleled the equipment that was already there. I mean, the high pressure lab and spectroscopy lab and scanning probe microscopy lab with a new lab for fabrication of solar cells and not solar panels, let's say lab scale solar cells. So now we are fully equipped for fabricating and testing the solar cells, and we are trying to contribute to that. So I'm going to the last slides of my talk, so let me acknowledge all the people working together with me at LTU and all the other collaborators abroad, and also the very generous funding agencies from Kempe Foundation to Wallenberg Foundation, LTU, Vinnova, just Swedish Institute to name the national ones. And is it possible in Sweden? Well, from the viewpoint of distribution of solar irradiation, that's not a good idea. But I think it's a very good idea developing here technologies that can be exported abroad. So I think that's a great idea. So thank you very much for your kind attention.
Thank you for that presentation. We have time for questions or discussions. Are there anyone who want to contribute or ask something? Please reach your hand, because we have to use the microphone so we get the questions or the remarks on tape. Then you start. Of course you do.
Okay, Håkan Lundbäck, interested in this technology. I would like to know, when do you expect the next generation of technology to reach the market?
It's a good point. I think I would say in the frame of years and less than 10 years. And I think the best parallel is with televisions. Probably you know that today you can find Samsung quantum dot televisions. Okay, quantum dot televisions are exactly based on the quantum dot I've shown before in solar cells. Let's say 5 years ago, it was absolutely incredible for scientists that quantum dot could reach the technology level of a market. And I think that at least in a couple of cases, like the perovskite solar cells, but also the copper indium gallium selenide solar cells that are already in the market but with lower efficiency, they can improve significantly. So I don't expect a revolution in the market and in the technology. I would rather expect new technology that can parallel the silicon with a decent efficiency, with a higher efficiency, and using more environmentally friendly materials. This is the perspective, I would say.
Anyone else? Yes.
So I have a question about the materials. You had cadmium in several of these molecules or compounds. And is it even allowed to use cadmium? And is it a problem for you?
That's a very good and controversial point of view. Question. For instance, I choose the example of lead, not of cadmium, but now I explain why. The most successful solar cells in the last 5 years in research are perovskite solar cells. Okay, and the perovskite crystal that is used as a light-absorbing material is based on lead. And they got 22% efficiency with using lead. If you don't use lead in this kind of solar cells, the latest results are around 3.5%. Okay, so if you look to the EU policies about polluting materials, the EU policy was not to fund any research which contains lead, at least till 3 years ago, because they wanted to be lead-free. Then it came this new generation of solar cells, and you cannot imagine the quantity of millions of euros that were invested from the EU in this kind of solar cells, which are containing lead. So from the environmental point of view, I fully agree with you. The cells that are containing cadmium are harmful. But I think that now the way the politics are deciding how to invest, it's pretty harder to understand. You should say we don't invest in perovskites because they are not lead-free. So, but they say that no, we can invest and we can try to find, for instance, ways to seal properly the solar cells. So let's fund now the fundamental research on that, and later on we can try to address the problem of environment. I don't say that's wrong, because, for instance, in quantum dots in television, it was the same. Quantum dot technology started developing on cadmium sulfide, cadmium selenide, and tellurides, and lead sulfide and selenides. But then, and it was roughly 15 years of research only on polluting materials. And then they came up with new indium-based quantum dots with almost the same properties, much more challenging to be synthesized. But now in the market you have televisions that are lead and cadmium-free. So that could be an option, yeah.
About carb?
It's on.
It's on. Is it?
Yes.
About carbon nanomaterials. So graphene versus carbon nanotubes. What is advantages, disadvantages of better one or another? Just from technological standpoint and capacity and.
No, I think probably you can reply better than me about that. No, but from the viewpoint of a composite materials, the challenge is dispersion. So we have experience in dispersing carbon nanotubes in titanium oxide mesoporous materials, and it works pretty well, and you are able to get a composite of these two materials. When we went to graphene sheets, it's at least in our experience, it was much more difficult to control the dispersion of a material in the composite. And one of the main challenges is also to investigate and detect these materials, because it's easy to detect graphene itself, but when it's dispersed in a matrix it's not so easy. So now research is addressing both the channels, carbon nanotubes and graphene. I cannot say what's better or not from the economic point of view.
But in terms of you have to decorate it with titanium,
yeah.
right? So is it any advantage of putting it on?
Well, for sure, I would say that you have an advantage when you have two-dimensional materials instead of one-dimensional material, because the specific surface is much higher. The drawback is that graphene tends to lie down in the solution, so you are not able to get a three-dimensional network of graphene, while it's very easy for carbon nanotubes in which you have an entanglement which very easily is self-standing.
You mean like forest? Like
yeah, forest. You can easily get a forest of carbon nanotubes, but at least I don't think there is a forest of graphene. Yeah.
Is there anyone else? No, I don't think so. We covered maybe not all, but part of it. Then we'll do like this. We'll wrap things up for this lecture. And first, I would like to start to thank Alberto for taking the time and making the effort to share this discussion with us. And I guess probably there will be further discussions on this later on as the research develops.
Thank you very much.
Thank
I'm
you.
honored at that. Thank you.
Thank you.
Thank you.